Good evening, good to see everyone. Today we have another science series seminar sponsored by CERN. We're welcoming today Dr. Howard Spero, the professor of Earth and Planetary Sciences at UC Davis. Dr. Spero is a well-known, world-known specialist in paleoclimatology, a lot of paleo things, right?
Paleoceanography.
Paleoceanography too, and a lot of other things. Dr. Spero is extremely widely educated person. He has degrees in geology, in biology, in oceanography, literally in almost all natural sciences. He authored or co-authored more than 130 papers. He is the director of the Stable Isotope Laboratory at UC Davis. He is a great, great teacher. That I can tell you from my own experience. Coincidentally, two people affiliated with with Berkeley City College have done their PhDs at UC Davis. Myself and Peter. You know Peter DeHaan, right? We both happen to be Dr. Spero's students, and we greatly, greatly enjoyed that experience. I can tell you even more. Dr. Spero, in fact, influenced what happens at this college a lot, because he inspired us to start the class on global climate change, which actually we now offer every fall. So I don't think that I need to introduce Dr. Spero anymore. You will hear by yourself what he has to tell us. Welcome, Dr. Spero, and thank you so much for being here.
Excellent. It's wonderful to be back. It's been a number of years since the last time I was here giving a seminar. I would like to say, for those of you who understand are students taking classes in paleoclimate, I can tell you when I was an undergraduate, if you had told me that I'd be standing here today, all right, giving a lecture on climate change and geochemistry and oceanography, I would have laughed, because there was no way I would have ever been able to guess where I was going to wind up down the line. So just remember, this is about the path, your education. And you're not directing it, it directs you. Okay, so I think the best way to start is just to say that, this is maybe a little bit rhetorical, but there is a little bit of a controversy in our country about climate and climate change. And the issue isn't about whether the Earth's climate system changes. Okay, we know that the geologic record tells us that climate has changed in the past. Many of the discussions and arguments come about where we are today and where we're going on in the future. And the purpose of this talk is to give you a foundation that allows you to take a look at the climate system from the perspective of 40 million years of Earth history. And to use that foundation and what scientists have discovered about how the climate system operates, how carbon dioxide interacts to amplify warming or cooling in the past, in order to understand where we are today, and then to ask yourselves the question, what is most likely going to happen tomorrow? Now, I'm going to take you on a trip, and that trip is going to go from decades back to millennia to millions of years back, and then we're going to take a little bit of a trek into the present, and I'm going to finish up, hopefully, with a lot of Q&A that will get you asking questions hopefully you haven't asked before, okay? Because I think that the debate that we're not having is a national debate we need to have. So I'm going to walk you through geochemistry, and I'm going to walk you through oceanography. But the best way to start, okay, is to start, how does the Earth operate? And when you look at the Earth, what you should see is a heat engine. Okay, it's an engine where sunlight warms the tropics, and heat's transported towards the poles, and at the same time, heat's lost from the planet. And we have seasons on the Earth today because the Earth is tilted. And it's that tilt that defines how much energy is striking the South Pole at some point in the orbit of the Earth around the sun, or how dark it is over the other pole, which would be Northern Hemisphere winter in this particular sense. Now, when you think about the climate system, it's important to keep in mind that we're dealing with a balance. Okay, we're dealing with a balance of solar energy that is making it to Earth, penetrating through the atmosphere. Some of it gets reflected by clouds, some by the surface, but much of the energy reaches the surface of the Earth and is absorbed. Now, the Earth itself re-radiates heat to space. We re-radiate infrared. And that re-radiation along its path, okay, some of it escapes to space, some of it's reflected, some of it's scattered, but a lot of it is absorbed. That infrared radiation is absorbed by carbon dioxide, methane, water vapor, molecules that have a bond type that allows those bonds to vibrate and absorb the energy in the infrared spectrum, the greenhouse gases. We could not live on planet Earth without greenhouse gases. They are absolutely necessary, okay? And it's the balance of heat loss and heat trap that gives us our current climate, okay? And it's really, really important to remember that when you go from the tropics to higher latitudes, okay, we have excess heat, okay, in the tropical areas. We have a heat deficit, okay, in the polar regions, okay, so you can see there's more net loss up here and more net gain, which gives us our thermal, our temperature gradient, okay, from the tropics out to the poles. If we alter the balance of heat loss to heat trapped, the planet is either going to cool down or warm up. It's that simple. That's the way the climate system operates. Now, this journey that I'm going to take you on starts right after World War II. And a group of researchers were working on a project called the Manhattan Project. Everyone know what the Manhattan Project was? Okay, we were trying to end World War II by creating the atomic bomb. And a group of researchers, Professor Alfred Neer at the University of Minnesota was there. This is a letter from Enrico Fermi to Alfred Neer saying, the new mass spectrometer that you built over at the University of Minnesota might help us to separate out uranium-235 for an atomic, well, he didn't say atomic bomb in the letter, okay, that was classified, but he was very, very interested in this new technique of mass spectrometry. So by the time we get out of World War II in the late 40s, the first mass spectrometers, a device that allows us to take elements and separate the isotopes of those elements based on their masses. Now, interestingly, another researcher about this exact same time, by the name of Harold Urey, who is commonly called the father of geochemistry, was working at the University of Chicago. And Harold Urey had just come up with a very, very interesting idea. And his idea basically said that if you look at different atoms, at different elements, we find that they have isotopes of different masses. Now, these are stable isotopes. They don't radioactively decay like carbon-14 or U-235, they are stable. We're all made of things like oxygen 18 or oxygen 16. The only difference is in the number of neutrons. And what he reasoned in a paper in the late 1940s and in a talk he gave to the Royal Society was that if we can measure the oxygen 18, oxygen 16 ratio in materials, we might be able to figure out what the temperature was when that mineral formed. You might be able to take a rock from the Sierras and figure out the temperature that it solidified. Now, at this time, Harold Urey had published this paper in Science, 1948, very famous paper. But he had a lot of graduate students and postdocs working with him at the University of Chicago. We have Harold Urey, we have Alan Lear, we have an idea, and we have a brand new instrument. Imagine being a graduate student in this laboratory. Nobody's ever done these measurements before. And the entire field of geochemistry arose out of this laboratory in the early 1950s. This picture was taken, it's actually taken when I was born, in 1953. It's Jerry Wasserberg up here, who recently passed away. He's a Caltech scientist. This is a young Italian PhD student, Cesare Emiliani. Now, Cesare had this crazy idea. And what Cesare said was, if we can measure the temperature of minerals, okay, can we use this technique to figure out the temperature on Earth's surface in times past? And what Cesare did, because he was a marine scientist, was he was aware of this incredible realm of planktonic organisms that float around the ocean. Okay, things like pteropods and diatoms, and they're just beautiful organisms. But one particular type was these critters right here that are called foraminifera. Now, these are single-celled organisms. They're marine protozoa, but they happen to make a calcium carbonate shell. And they are prolific. They live everywhere in the surface and even in the sediments of the oceans. And they make this calcium carbonate shell out of calcium, carbon, and oxygen. And what Cesare hypothesized was that if you measure the oxygen isotope ratio in these shells, you might be able to figure out the temperature of the ocean when the animal grew in the past. And since the deep ocean is covered with the shells of these organisms, trillions and trillions of these shells everywhere, if you take deep sea cores and you pull the mud up and you slice up the core, you can go back in time. You could be a time traveler and you can figure out what the temperature of the ocean was in the past. Has climate varied? And that's exactly what he did. Okay? And he published a paper in 1955 with the title Pleistocene Temperatures. Very first paper in paleoceanography. And what he discovered was fascinating. If you take a look at the oxygen isotope record that he generated, the values change. They look like basically a metronome beating. And based on the fundamental principles of Harold Urey, he was able to argue that we go from interglacials to glacial periods, to interglacials to glacials, and so on, going back in time. But the problem was that Cesare didn't have time. He had depth in the core. He didn't know what the time was. He just knew that the surface ocean, in this case in the Caribbean, was cooling and warming, which he reasoned from a lot of other research that had been done in the early 20th century, that this was due to climate change on planet Earth in the past. And in many ways, this started the field of paleoclimatology and paleoceanography. Because from this point forward, we have been chasing the fundamental question, what causes climate to change? We have the evidence, we know it does, so what causes it? Fast forward 70 years, and we've done an awful lot of measurements in that time. And what you're looking at here is a 40 million year record of the Cenozoic. The last 40 million years. Over here is 65 million years ago. Those are dinosaurs, dead dinosaurs. They got hit by a meteorite. Okay? So what we find, if you look at this left axis, is that the oxygen 18-16 ratio, okay, and this turns out to be bottom-dwelling foraminifer, benthic foraminifer, it tells us that 35 million years ago and further back, the Earth was incredibly warm. Matter of fact, there was no ice on any of the continents, and the deep ocean temperatures were so warm that they were warmer at the bottom of the ocean than Monterey is in the summer. Okay, really, really warm. And then abruptly, about 33 million years ago, at the boundary between the Eocene and the Oligocene, what we find is a dramatic change in the oxygen isotope record, and everything shifts towards the cold end. And we now know that what was happening in the background was plate tectonics. Continents were shifting around, Australia and Antarctica were moving apart, and South America and Antarctica had just separated. And they formed a gap. We call it a gateway. That started the circumpolar current that flows around Antarctica today. And that opened up a period of time where Antarctica glaciated. That's where we see the first glacier showing up on Antarctica. And then you can see through the Oligocene, things are cold, then they warm up in the Miocene, and then from about 10 million years to the present, this is an inexorable decrease in deep water temperatures as we move to the present, where we have the coldest temperatures in the deep ocean of the entire Cenozoic. And as a matter of fact, if you go back through the age of dinosaurs, this is actually colder than at any time during the entire age of dinosaurs back 250 million years ago. So it's an ice house world. We live in a glaciated world. Now, this is sort of the eagle's view of climate change. But let's take a look at maybe the last couple million years, and let's see what happened with climate. And this gives us a hint as to the mechanisms that are driving the climate system other than these huge tectonic events, which happen on millions of year timescales. So if you go into one of these cores, and now, of course, as I said, we've got 60, 70 years more data than Cesare and Miliani had, and you take a look at this oxygen isotope record, going back, in this case, this record here goes back 1.8 million years. What you see is this constant beat of climate, okay, as we go back in time. And there have been changes. It looks to me like the frequency's changed here relative to what it is over here, okay, but the beat's there. It's constantly beating. And this became a real big problem to try to figure out what is the pace setter, what's that metronome beat that's causing climate to change. And it turned out we had to now go to an entirely different field, the field of mathematics. And a Serbian mathematician by the name of Milankovitch in the early 20th century had published a seminal paper that said he thinks, based on mathematical calculations, that the Earth's climate system changes with changes in the Earth's orbital configuration around the sun. How much sunlight is striking the northern hemisphere at different times, okay, in the past. And in effect, what he was talking about were three specific cycles that exist today. We know they exist. One of them is related to how elliptical the orbit is around the sun. The sun's ellipse, the Earth's elliptical orbit shifts back and forth through time. So when it's closer to a circle, okay, the distance between the sun and the Earth at any point in the orbit, okay, the difference gets smaller. And the larger the ellipse, there are times where the Earth can be close and the Earth is a lot further away from the sun because, remember, with an ellipse, the sun wouldn't be in the center, it's off to the side at what we call the focus. And what that means is as the ellipse moves back and forth, we now see these oscillations in the amount of sunlight that strikes Earth. And it turns out these are on 100,000 year cycles, and there's also a big 400,000 year cycle in there. But he also pointed out that the Earth's tilt changes. Okay, and that changes back and forth. And why is tilt important? Because the more tilted over the axis is, the more direct sunlight the high latitudes get. So when the tilt lines up and it goes less, it gets colder at the poles. And because of that, we get this beat that's turning over here, which turns out to be about 41,000-year cycles. Finally, what we have is a third cycle. The Earth's orbit around the sun is set by this ellipse. But as the Earth is spinning through time, the Earth's axis wobbles. And basically, if that's where the North Pole is, it's just pointing, it's wobbling like a top that's starting to slow down. And this wobble places the northern hemisphere summer in different places around that orbit through time. And that's a 22,000-year cycle. So if we take a look, now a close-up look at the climate system, and we look at the last 250,000 years of that long 1.8 million record I showed, you can see what we call precession, these 22,000-year cycles. Here's the wobble. So today, the axis of the Earth points to Polaris, the North Star. In 11,000 years, we're going to be pointing 44 degrees, 45 degrees away from Polaris, just because of this wobble. Okay? So we have this 22,000-year cycle. Here's our 41,000-year cycle, 41 and 41. And of course, there's your 100,000-year cycle. So the data that we collected from the deep sea and all the records consistently draw out these three Milankovitch cycles. And the climate system seems to be paced by how much sunlight is striking the Earth depending on orbital shape, tilt, and wobble. Okay? But, very important, these are operating on tens of thousands of year time cycles. Very long time cycles. Okay? The transitions even are on the orders of 6,000 to 7,000 years. So we're always dealing with millennia, thousands of year times, shifting climate around in the natural sense. Now, while the study of the deep sea was going on, there was another group of researchers from the US and from Europe that decided to spend their summers up on the top of Antarctica, drilling cores in the ice. They weren't drilling them in the deep sea muds, they were drilling them up on the ice. And these cores were collected, and then they were analyzed. Now, it's really hard to imagine how deep the Antarctic ice sheet is, how far it is from the surface down to the bedrock. Okay? I think Donner's Summit is 7,200 feet. Is that about right? 7,200 if anybody's going up skiing in Tahoe. Okay? The depth of the ice over Vostok, which is one of the deeper areas over Antarctica, is 4,000 meters, which is in excess of 12,000 feet. Okay, so if you think of the Sierras, add another 70%, and that's the depth of the ice core. There's a lot of water and a lot of ice up on Antarctica. Okay, but that ice has been accumulating for a long, long time. So by drilling down into the ice, you have the ability to look at the history of Antarctic temperature and climate going back in time. And we've done this with a number of cores now, and we now have a million-year record of what Antarctica has been doing at the same time that the deep ocean's been operating. But more important, as that snow that falls on the surface freezes and hardens into ice, it traps air bubbles. And the air is the atmosphere that existed a million years ago, or 500,000 years ago, or 50,000 years ago, which means you can take that air and you can analyze it for its greenhouse gas content. Now, prior to the ice cores, we could only hypothesize that greenhouse gases must be doing something to climate, okay? But there was no evidence. And then the ice core group published their records. And lo and behold, This is now another type of isotope geochemistry on water. This is ice. This is giving us the temperature record. Okay, it's actually the oxygen isotopic composition of the water. All right, and below it is the CO2 record. All right, and you can see down the bottom, these are in hundreds of thousands, so this is an 800,000-year record of CO2 and Antarctic temperature. And what you should notice is we are in an interglacial. It's a warm period. So here we are today. Shows the exact same thing that we see in the deep sea records. And CO2 levels, okay, in Antarctica, basically before the Industrial Revolution, is in these cores, okay, was about 280 to 300 parts per million. So at one of these interglacials going back about 400,000 years, we hit about 300 ppm. So the interglacials have high CO2, and when you get into these glacial periods, they have low CO2. The greenhouse gases increase and decrease in sync with climate. Now, of course, what's the big question? The big question is, does the CO2 drive climate, or does the climate somehow drive CO2? Okay, and this became an extremely hard problem to tackle, but we solved the problem. How did we solve it? A lot more geochemistry, a lot more analyses on high sediment, on high accumulation cores, and what we discovered, if you just take a look at the last 20,000 years, okay, in an ice core that's off on the West Antarctic ice sheet, that when we get into the last glacial, LGM stands for last glacial maximum, 20,000, 22,000 years ago. Things were really cold. So here's our, in yellow dots, that's our CO2, and red and blue are temperature. But red is the temperature of Antarctica. Blue is the global temperature, collected from all over the northern hemisphere and elsewhere outside of the southern hemisphere. And what you see, and it's a little hard to see, but it should be obvious when I point it out, we are basically coming forward in time until something about 17,800 years ago. Or to put it differently, 16,000 BC. Okay, if you want to think of it in terms of BC. And these red Antarctic temperatures start to rise. And what you'll see is the CO2 lags. The CO2 starts rising after Antarctica starts warming. Okay, you can see the little gap in there. I'll show you another plot in a second. But look at the northern hemisphere and the rest of the world. The CO2 starts rising. Meanwhile, there's this huge lag in the northern hemisphere. There are huge ice sheets on North America. There are huge ice sheets over on Europe. It takes another 700 years to 1,000 years before the northern hemisphere starts to warm up. And it's too fast for anything Milankovitch to be kicking in. It's the greenhouse gas warming of the atmosphere that starts to warm the northern hemisphere. So Milankovitch, because of the alignment of obliquity, of precession, of eccentricity, starts to warm Antarctica, and something happens, and then CO2 starts to rise about 500 or 600 years later. And as CO2 mixes in the atmosphere very, very quickly, it then starts to warm the northern hemisphere. Now, what was that thing that happened? And right now, we have a pretty good theory at the moment of how this works. And the idea put forward, if you know your basic wind systems, hopefully many of you have taken oceanography or climate, and you've talked about the westerlies and the trade winds and things like that. Here is our circumpolar current that's going all the way around Antarctica. And this happens to be in an area that's referred to as the Roaring Forties. It's the worst weather in the world. The westerlies are just blowing completely around Antarctica like this. And while they do, they mix up the ocean and they upwell water from deep inside the interior of the ocean. Now let's step back a little bit in time to the glacial period. When we had the glacial period, the planet was so cold that sea ice extended all the way out to probably about 1,000 kilometers north of the Antarctic continent. And with sea ice over the ocean, the westerlies were pushed all the way up, and all this deep water, which is rich in CO2, CO2 that's accumulated from the microbial community breaking down the flux of organic matter into the ocean and respiring, all that CO2 in the deep ocean was sequestered there. And it was sequestered for 90,000 years, basically the development of the whole glacial period. And then Antarctica warmed up. And as soon as it warmed up, the first thing that goes is the sea ice, just like it's going today. And that opened up this entire ring. And about 300-400 years later, we start mixing up the CO2 and it starts belching out into the atmosphere, and CO2 levels start to rise. And the northern hemisphere follows. And if you take a look at Antarctica and the northern hemisphere, here's the data. This shows when the CO2 rises, and it shows the southern hemisphere on average, and all the data and all the locations in the southern hemisphere, that it warms about 600 years before the CO2 starts to come out. And the northern hemisphere in the global system warms up 500 to 800 years, lags the CO2. CO2 is an amplifier. Very, very important. CO2, okay, amplifies the effect of solar warming, of solar insolation. It traps more infrared and it warms the planet. But the CO2 on the natural cycle is either sequestered deep in the ocean, okay, until it's allowed to come back out, usually in the Southern Ocean is the big area, but we have other upwelling zones around the planet where CO2 escapes. But the Southern Ocean is the big location where CO2 comes out of the ocean, the deep ocean, thousands and thousands of feet below the surface. So when we take a look at the marine record and at the ice core record, the important information that you should get out of this, okay, is first of all, the system naturally changes, but changes slowly. Thousands of years to move from glacial to interglacial. It's the insolation cycle that's the metronome, that's beating, okay, that's helping to pace the growth and the shrinking of the ice sheets. Okay? Importantly, the natural CO2 system that we see from the ice core records, 800,000 years, the planet has been operating in a very narrow band of greenhouse gas concentrations. Okay, there's only about a 100 part per million change between the glacial and the interglacial. And we see this time again, every time we go through one of these glacial cycles according to the ice cores. And the other is that the CO2 is stored in the deep ocean. Okay, this is the natural cycle. All right, so with this in mind, let's take a look at something and ask the fundamental question. Okay, if the climate system changes as slowly, okay, and given that we're in an interglacial, and if you look at the record, it pretty much says we should be starting to go into another ice age. Okay, but we don't spend much time in those interglacials, and they drop into another ice age. Remember, every one of those 100,000 year cycles, 7 to 10,000 years in a warm period, 90,000 years growing a glacial, the glaciers, and then we pop out. We should be going into another ice age, which is what the scientific community thought 40 years ago. Why, then, is the scientific community so concerned about what's going to happen over the next century? And it comes down to a few things. And this gets into questions about where the CO2 is coming from. The first is that the rate of CO2 increase in the atmosphere today is unprecedented. It's going in very, very quickly, okay, into the atmosphere, wherever it's coming from. We'll get to where it's coming from in a little bit. The source, some have argued volcanism, volcanoes. Others have argued it's human activity. Is there a way to separate this so that there is no question about where the CO2 is coming from? You can't argue that, well, you know, the planet's been operating a long time and this is unnatural. You have to have solid scientific evidence to say it's definitely not volcanism. And the other problem, and this one gets down to some of the fundamentals, given the way the climate system operates, it's unable to mitigate the greenhouse gas input that is going into the atmosphere today at its current rate. It can't handle it, which means CO2 accumulates. So let's take a look at what the CO2 system looks like, and let's talk about what happens. So we're all familiar with the Vostok CO2 record. You probably haven't seen this animation. If you have, bear with me. It's about 3 minutes long. And what you're looking at now is the year-by-year oscillations in CO2 on the planet. And every one of these dots is a station that's collecting CO2 data. This is the northern hemisphere, and there's Antarctica in the southern hemisphere. And they call this the pump handle for obvious reasons. Okay? Why is the CO2 going up and down in the northern hemisphere and is not doing very much in the southern hemisphere? Do you guys have a good idea? Well, there's a lot of ice down here, but why is that happening? Well, you're on the right track, but it's much simpler than that. Where's all the land? It's all in the northern hemisphere. And what are we really looking at? Why is it going up and down like this, these oscillations? Because when it goes down, we're in spring. And the trees are leafing out and the plants are taking up CO2. So the CO2 drops. And then in the fall and the winter, CO2 rises because the leaves fall and the microbes break them down and CO2 goes back into the atmosphere. So that's what the natural cycle of CO2 is on the planet. The thing that's very disconcerting is this inexorable rise in the CO2 levels. Okay, and this is part of that Vostok core that we've been talking about. You'll notice, what was the range that I said? 180 to 280, 180 to 300 ppm for glacial, interglacial. Okay, well, we just hit 400. Okay, these CO2 levels don't appear in the ice cores. But now let's attach this to the ice core record. Okay, so now we're going back in time to the beginning of the Mauna Loa CO2 record that Ralph Keeling started up on in Hawaii, 1959, and we'll attach that to an ice core that was collected in mountain glaciers, a very fast accumulating record, to show that if you get back to about 1750 to 1800, our CO2 levels are back where they were in the ice cores. And now if we attach this, we're going through basically Roman times here. You'll notice not a lot of perturbations. We know that European forests were being deforested during this time. CO2 didn't perturb. And now we start attaching that record onto the ice core records. And you get a sense of the rate of change that we've had over the last 150 years relative to the background history of the ice cores. Okay, so now we're one glacial cycle, we have a second glacial cycle, and so on going back in time. We are definitely out of whack somehow. So what is the source of this CO2? Okay, and how confident can I be that the source is really the source? We all, most of us, many of us, I'm sure, think it's fossil fuels. But if you ask me, how do you know? That's a tough one. And to go and figure that one out, we have to go back to Harold Urey's lab. And instead of looking at oxygen isotopes, what we want to do is look at carbon isotopes, another set of stable isotopes. We're all made of carbon-13 and carbon-12. Matter of fact, about 1% of the carbon in your hair and your skin is carbon-13. And it turns out that the carbon-13, carbon-12 ratio is a very sensitive indicator to biological processes. Now, when this ratio increases with more C13, what we find is that a unit that we call delta values, I'm not going to go into the geochemistry, it gets positive. It means more C13. And when it's negative, it means less C13. Just think of it that way. So what does the world look like in carbon isotope space? Well, if you look at plants, okay, these plants minus 25, minus 26, very negative. They don't have a lot of carbon-13 in them. Relative, +1, that's about the ocean's carbon. About +1. So very, very large difference between organic carbon, methane, minus 50. Really, really negative. Now look at the atmosphere. The atmosphere is about minus 6. We measure the carbon-13, carbon-12 ratio of the CO2 in the atmosphere. And the reason this is minus 6 is because most of the CO2 in the atmosphere is interacting with the ocean surface. And there's exchange between the CO2 that's down in the ocean and the CO2 that's in the atmosphere, moving back and forth. What's oil and gas? Oil and gas are basically plants that have degraded to produce hydrocarbons, whether it's gas, whether it's oil, or whether it's coal. So you would expect the delta C13 of gas and oil and coal, if it was being burned, to have a carbon isotope value that's very negative, and what it should do is it should shift the carbon isotopic composition of the atmosphere in a negative direction. What about volcanoes? Now, this is a very gutsy researcher that went up to Mount Etna and measured the CO2 coming out the vent on Mount Etna that sits basically on Sicily. And what they found was that the carbon isotopic composition of the CO2 belching out of volcanoes, coming from crust and coming from the mantle, has a delta C13 somewhere between -1 and -5, or say -3. Okay, so if it's -3, well, actually, I think go this way. If it's -3, that's more positive than -6. So if volcanoes were the source of CO2, what we should see in the ice core record should be a carbon isotope ratio that's moving in a positive direction. And if it's organic, it should be moving in a negative direction. It's that simple, and it really is. Now, where's the issues that come up when we go online, okay, and you ask fundamental questions? Well, first of all, do volcanoes affect climate? All right, and the answer is yes, but they only do it occasionally. And when I say occasionally, I mean occasionally. The last time we had a volcanic event that affected atmospheric CO2 to a large degree was 17 million years ago. And this was the Columbia River basalts, the big basalt flows that you see if you drive up to Oregon and Washington along Interstate 90. You go down the Columbia Gorge, those are all volcanics. And it turned out that this is all due to the fact that North America used to be over the hot spot, that plume of superheated mantle material that's now sitting underneath Yellowstone. But when it's under Oregon and Washington, it just had this outpouring of lava. And you can see as you go back in time, billions of years, there's been probably about 15 major events. There was one very, very close to the extinction of the dinosaurs, which I think might have been pushing the climate system, and that's one of the reasons the dinosaurs went out as easily as they did. So there is times when the amount of carbon dioxide and other greenhouse gases can enter the atmosphere with volcanism, but they're very infrequent. If you take a look today, okay, here's all those events, those very large events up here. If you look today, what we find is that the volcanic emissions are about 1% of the current rate of CO2 increase in the atmosphere. 1%. So we're not dealing with a lot of volcanic activity today. Now, I was searching the web before I came over here, okay, and finding cartoons. Okay, this is just one that says it's 1%. And I came across a very, very interesting blog. And this poor soul, okay, has it titled 3 Million Underwater Volcanoes. And his argument was, I've done the calculations. Okay, and I can tell you that the amount of CO2 released by volcanoes, if you include all the volcanoes along the mid-ocean ridges, is a couple of orders of magnitude higher than is published. In other words, about the size of the CO2 emission that's going on today. There's a couple of problems with that. Okay, the first is that when you look at oceanographic measurements, you would see this. That's a lot of CO2. And we don't see it in the deep sea, even near the hydrothermal vents. Okay, and we don't see any change in the carbon chemistry of the deep ocean. So it's tough to say that this can explain this. But more important, there is no direct connection between the deep ocean and the atmosphere. It takes thousands of years for the ocean to overturn. Okay, and right now we're seeing something that's operating on decades to centuries. So what happens when you look at the Antarctic CO2 record and we look at it in carbon isotope space? Okay, so here we are with atmospheric CO2 levels. This is thought to be emissions. Okay, is measured by, calculated by a number of people. What does the carbon isotopes do? Well, to answer that question, which is the first time it was really answered, we have to go look at a recorder of carbon chemistry. And they turn out to be things like coral reefs, or in this case, what we call a sclerosponge. It's a calcium carbonate producing sponge that lives in the Caribbean. It lives in caves. It's a cryptic fauna, as they call it. And they grow really, really slow. So this is sort of like a tree ring. And a group of researchers in Germany analyzed the carbon isotopic composition going back from 1350 AD to the present, and you can see nothing really was happening until about 1830. And then in 1830, the carbon isotope composition of that calcium carbonate skeleton began to decrease precipitously. The surface ocean is in contact with the atmosphere. But really important, even though we know that during the Little Ice Age and during the early periods of Roman occupation, we were deforesting Europe. We were burning everything. We were burning all the trees for fuel. We don't see major changes of any significance for the first 500 years of this record. There's not a lot happening until the Industrial Revolution. This is what it looks like when you plot CO2 against the carbon isotope record. It's quite clear that the values are decreasing, which says it's organic. It's organic carbon. It's not volcanism. Now we can argue where that's coming from, but it's organic carbon. Okay, this here negates a lot of the big arguments about where the CO2 is coming from. It's human activity. There's no other way to explain the chemistry of that CO2. And I say that with a lot of confidence, because if I look now at the ice core record going back 20,000 years, this is now 20,000, 25,000 years. Okay, remember we have all this change in CO2. This is what the carbon isotopic composition of the CO2 in those ice core bubbles is. And you'll see that it only ranges from about minus 6.5, minus 6.2, tiny, tiny range. Here's where we are today, minus 8. There is no way to get from here to here unless you add carbon with a very negative carbon isotope value, and that is hydrocarbons. So I have 3 more slides. This is what the atmosphere looks like since 1975. And on the left axis, you can see the carbon isotope values. That's minus 7.4, that's minus 8.2. That is 9 different stations around the planet, and they all show this continuous decrease in these ratios. The organic carbon is the source, which presumably is fossil fuels. Okay, so let's just finish this up today and we can open this up to Q&A. Okay, so what can we say with a lot of confidence? Okay, we can say with a lot of confidence that the natural climate system on Earth changes very slowly. And it changes due to Milankovitch cycles and the amount of insolation, okay, that's striking the high latitudes. The cycles operate on tens of thousands of year timescales. It's slow. It's not fast. CO2 is very, very important in the planet's shifts from one climate state to another, but it's not the driver, it's an amplifier. If you add CO2 to the atmosphere, you start to trap more infrared radiation and you warm the planet. That's what the natural climate system tells us. High greenhouse gases, things are warm. Low greenhouse gases, things are cool. The CO2 that's entering into the atmosphere has a chemical fingerprint, okay, that points to burning organic carbon, not to volcanic carbon. It can't be volcanoes that's causing this. And the other thing, and this is the one where this really leads hopefully into the Q&A and the scary part for the scientific community, the rate at which CO2 is entering the atmosphere over the last 60 years is 100 times faster than it ever does when the planet naturally comes out of a climate shift and that CO2 comes out of the ocean. So it's 100 times faster. The ocean and the other systems on the planet can't handle the CO2 rate at which it's coming out now. So what can we do? Okay, and I intentionally made this very, very short so we can open this up to Q&A. It's really, really important to understand the science that's underlying our climate system. Okay, it's well-founded. The scientific community is not trying to pad their wallets, as some have claimed, by getting NSF awards on taxpayers' back. Okay? There's a lot of very careful scientists that care about what's going on, are concerned about what's going on. The science is solid. We've entered a period of time where the rate of greenhouse gases exceeds the capacity of any system to absorb those gases, which means the atmosphere's heat absorbing capacity is increasing. The only question is what's going to happen in the future, which is where models come in. And I've intentionally not dealt with models because I don't necessarily think it's important for the dialogue that we have to have in this country, because we are dealing with a multi-generational problem. Okay? We are dealing with a problem. The actions that we take over the next couple of decades are going to have very little effect on half of us, especially anybody in here with gray hair, okay? And for the rest of you, there's even a chance that when you have gray hair, people are still going to be arguing about this, all right? But I can tell you that your kids and your grandkids are in for a really interesting ride in the future, all right? So the national dialogue that I think that we need to have has to come from the foundation of understanding the climate system. And then we can talk about what we want to do with it. Because really, I don't have any kids. I could be very selfish. Hey, that's not my problem, okay? All right? But I do care about our future, and I do care about society's future. And we're on a planet where the carrying capacity is getting pretty close to our population. Okay? And regardless of what happens, whether things warm up or cool down, any change in climate, in the hydrologic system, okay, in aridity, right, in heat, in sea level, any change is going to have incredible impacts on people in other parts of the world that are sitting in countries that are 1 foot above sea level, that are sitting right on the edge of the Sahara, where a slight expansion of the Sahara means no food, Just take a look what's happening in South Sudan. Okay? So we need to have this conversation, and we need to have it soon so we can figure out what we and the rest of the world are going to do about it. So I think I'm going to stop with that and open it up to Q&A. So thank you. Yeah. I think there's microphones on the side too, but you can try to scream out. Yeah. The tilt is 41,000 years.
Does it mean the seasonal also change, like summer become winter?
So the question that's being asked is a good one. And normally the Milankovitch lecture is like an entire talk unto itself. But the best way to think about this is we have the Earth's orbit going around the sun. And if the Earth is tilted like this and the sun's here, this is northern hemisphere summer. And then when we're on the other side of the orbit, it's northern hemisphere winter. So this is basically December, and this is June. But because of the fact that the Earth's axis wobbles, okay, it's possible if it's 11,000 years from now, the axis is pointing this way because it's wobbled around. So when it's in the exact same place that we have summer today, 11,000 years ago, that's going to be winter. And then on the other side of the orbit is going to be summer. So if we have a big ellipse, and there's a large distance difference between the close approach and the further away approach of the Earth to the sun, it's important whether our northern hemisphere winter is when we're really, summer is when we're really far away, or when it's really close. And that's what affects the amount of sunlight that's going to strike the northern hemisphere, okay, and warm up the ice sheets or melt the ice sheets. When we're closer and we have a northern hemisphere summer, okay, they're going to melt. Now the other thing that's important, of course, is the tilt. Because if that aligns with a large tilt, then you're actually getting more direct sunlight at the exact same time. Versus when the tilt is standing up, there's not as much direct sunlight on the North Pole. So what happens is these three cycles have interplay, and when they align up, you get a collapse of the ice sheet. And then the next time they align is 100,000 years later, you have another collapse of the ice sheet. And in between, you have partial collapses as the tilt plays a role. So that gives you the Milankovitch sort of story.